I'm working at the laboratory for meteorological studies in Clermont-Ferrand, France. And we are here on this ship, which is the Tangaroa in New Zealand, Wellington, in the frame of the project SEA2CLOUD, which aims at understanding what are the relationship between the ocean and the particles which are emitted to the atmosphere, and how these particles will ultimately modify the cloud properties, either by acting as a cloud condensation nuclei or acting as an ice nuclei.
So you switch these around, did you?
Yes.
And so they just have to be aware of that bit.
So I can check.
And I don't think that will be a trick problem, because I don't think people will walk that way round. If you come from where? They can come up here and then go round. We just mark off the zero.
So the campaign is going to take place east of New Zealand. We chose this area because it is free of anthropogenic pollution, and we can better understand the relationship between the ocean and the atmosphere.
Jacket, you've got a light, the blue thing, that's automatically activated when you get in the water, and then with a push button you start it going.
And welcome aboard the Tangaroa. My name's Mark. So as I said, the two primary roles that I have on my voyage are to keep you safe and to complete operations in that order. So at any time, if anybody feels unsafe or they feel uncomfortable with the operations that we're having, please let your head of department know, or in a worst case situation, any time you can stop the job. So safety is our primary role. Thank you very much.
So there's been these theories around for decades now about how the fact that the plankton that live in the surface ocean can actually influence the composition of the atmosphere, and that affects the way it produces clouds. And so we're basically going out to study that. So we're looking at the plankton in the seawater and then the atmospheric composition in the air overlying the ocean.
The experiment that we will perform on board will be to generate sea spray from the seawater and to measure the properties of the seawater on one side and the properties of the sea spray on the other side, understand how microbiology in the seawater will influence the sea spray properties and then the formation of clouds above the ocean. Another experiment will be to have large enclosures on board in which we have about 1,000 liters of seawater enclosed and 1 cubic meter of air above, which will be closed, and then we will measure fluxes from the seawater to the atmosphere continuously on board of the ship. We want to have different kinds of phytoplankton populations, so this is why we are cruising through these different areas of the ocean east of New Zealand.
Donc là, cet instrument, il va faire différentes mesures. Il va faire une mesure dans l'air ambiant, donc tout autour de nous, et 2 mesures dans les 2 cylindres qu'on a juste devant le container. Donc il y a un cylindre où il y aura l'air qui va rentrer, on appelle ça un flush. Il sera essentiellement composé d'eau de mer, et celui-là, on ne lui ajoute rien du tout. Le deuxième, c'est exactement le même avec de l'eau de mer, sauf qu'on lui rajoute de l'ozone. Parce que l'ozone peut réagir avec les composés organiques volatiles et sûrement en produire plus ou moins.
Je m'appelle Laurent Labonnotte, je suis enseignant-chercheur au laboratoire d'optique atmosphérique à Lille et je suis venu sur cette campagne de mesure SEA2CLOUD pour amener 3 instruments du laboratoire, donc un radiomètre infrarouge, un photomètre solaire et un radiomètre visible qui fait des mesures en polarisation. Alors ces instruments ont été installés sur le toit du bateau, ce qu'on appelle le Monkey Island, et ils sont en fait protégés de ce fait des embruns qu'il peut y avoir ici, parce que bon, ça souffle quand même un peu, et puis un peu protégés également de ce que rejette le bateau en gaz d'échappement. Alors le photomètre est principalement utilisé pour caractériser la composition de l'atmosphère en aérosol, et les 2 autres instruments sont plutôt utilisés pour caractériser la composition en particules, donc en taille de particules et en quantité d'eau, des nuages liquides et des nuages de glace. Alors tout ça pourquoi ? Pour essayer de voir s'il y a une corrélation entre ce qui est mesuré au niveau de l'océan et ce qui est émis par l'océan et la composition de l'atmosphère en aérosol et en nuages.
Je suis Frédéric Perrin, je suis ingénieur en instrumentation à l'Observatoire de physique du globe de Clermont-Ferrand et sur la mission Tangaroa, je suis en charge de plusieurs instruments atmosphériques dont le radar et le lidar. Ces instruments sont là pour mesurer les paramètres atmosphériques de la mission, donc tout ce qui se passe au-dessus du bateau, savoir si on a des nuages, si on a des aérosols ou des particules en l'air.
Hello, my name is John Schublat and I'm a postdoc for LAMP in France. These aquariums take the seawater and they replicate the action that occurs when waves break in the ocean, and that creates bubbles, and those bubbles then burst at the surface of the water, which creates the sea spray aerosols, the tiny particles. And we have a bunch of different instruments that are then taking those aerosol particles and measuring them for different things. this gives us the number of particles and what their sizes are. And down here we have our 2 filter collection samples.
I'm Mike Harvey. I work at NIWA in Wellington in an atmospheric group, and I'm very interested in the way biology kind of interacts with the climate, and so this voyage has been a really good opportunity to bring a whole load of experts together, I think, to investigate that sort of issue. So we're launching weather balloons on this trip twice a day, and it's really mainly to verify model results of the wind, so that we can sort of in post-processing really look at where various air masses have come from. So it's quite useful for us to know what degree of influence there is from both terrestrial and sort of natural background environment out here where we're sampling. Yeah, okay.
So are we going to launch it from the front of the boat?
Let's see where the wind is when we're out. I'm not sure what the wind's coming in.
Yes. I think he wants to go this way. So like some of the green, some more of the green stuff.
Yeah, more of the chlorophyll. More of the chlorophyll.
Yeah. So yeah, we're coming around.
Okay.
We'll be steadied up by the time you're on deck.
Yeah. Okay. We'll go and fill, and they'll spin round, and then we'll launch from the front.
Yeah.
Okay.
We pick up 2.
Channel 3, Channel 2, Channel 1.
Hello, Mike.
Yeah, thanks, John.
Great. I'm John McGregor. I work for NIWA, and I'm on the ship here. I'm doing atmospheric measurements, mainly wind sonde, weather balloons, and also the sun photometer. I'm Mike, John here. Yep, signal is good. We're just getting a GPS lock now. I'll just confirm as soon as we get up speed. Yep, okay, it's moving at 1 meters per second. We've got a good GPS, so it's ready to launch when you are.
Okay, thanks, John. Yep, the sonde is on, and we're finally on the foredeck.
As the balloon rises up into the atmosphere, it's continually measuring pressure, temperature, humidity, wind speed and direction, and transmitting those values back to this receiver.
Give a countdown. 5, 4, 3, 2, 1. Oh, gust speed. That'd be good.
More interesting than yesterday.
Yeah, it's gone. I really want to go. I think we were the right size.
Yeah.
We'll see what the ascent rate was.
Okay, the red curve is the altitude of the balloon, which is steadily increasing. The blue curve is the rate of ascent in meters per second. So here's temperature, it's steadily decreasing with height. So once it gets above about 400 meters, the wind is veering off.
So because we're needing to know how much aerosol there is in the atmosphere, we've got this instrument that does a column measurement looking at the sun at different wavelengths, and so we can compare that with aerosol measurements that have been made elsewhere around the world, and look at how that's impacted by the local conditions here, how windy it is. So we're going to be doing this throughout the voyage, kind of measuring when we've got good sunny, bright conditions.
Hello, my name is Godfrey. I'm the cook here at Tangaroa. Welcome you guys all. Thank you.
Very good.
So my name's Lila and I'm the steward on the Tangaroa.
So when we launch the boat, the crew will be launching and it'll be down at the cutaway that will be swinging around. It's going to be for about a voyage of about sort of 2 hours. So when you guys go away, obviously we'll be keeping Tangaroa the other side of the current. We want everyone to be wearing hard hats, so we've got for the science team some climbing hard hats down there. These ones got good straps underneath, and these are just to protect you for when the boat goes in the water. The hook that's taking the load goes slack and can then move around a little bit.
Yeah. Okay, cool.
Okay, Pete. So that's out of the way.
Okay.
So does that mean I change the zipper?
How's it looking?
No, it's not. It's a little bit pointing that way.
Some water.
Hi, I'm Teresa Bartemes, and I'm working in, actually, like, my lab is in Germany, so that's in Kiel, and I'm working with Geomar, so I'm doing my PhD there. And I am joining this voyage because I'm, like, for my PhD I want to specify the properties of the sea surface microlayer, which is the uppermost, like, surface of the ocean, And how we normally do that is like we go on a rubber boat, like on the working boat, and I dip this glass slide into the water, and through surface tension the water is going to stick, like the water from the uppermost surface is going to stick on the glass slide. And what I'm doing here is like preparing my samples for analysis, which is not happening on the boat but at home, so I will transport them back to Germany. And what I'm going to analyze is like amino acids and carbohydrates, and these are like my most sensitive parameters, so that is normally what I prepare first, and then I store them at -20 degrees to make sure that like the biology is not continuing and that everything which is active stops.
Alexa Samakari. Je fais ma thèse à Niwa en Nouvelle-Zélande et je fais partie de l'université néo-zélandaise aussi. Et Clifflo me supervise. Donc ma thèse concerne la dynamique du DMS et DMSP dans la surface de l'océan. DMS, c'est diméthylsulfide. C'est un gaz qui est issu du DMSP, diméthylsulfonopropionate. Donc le diméthylsulfonopropionate, DMSP, est produit par le phytoplancton. Et ensuite, dans l'eau, par certaines réactions, il se transforme en DMS. Et ensuite, ce DMS, qui est un gaz, est émis dans l'atmosphère. Et une fois dans l'atmosphère, il est oxydé et il contribue à la formation des nuages. Donc sur le bateau, pendant ce voyage-là, à SEA2CLOUD, je m'en vais dès que les conditions climatiques sont favorables. Donc ça veut dire pas de pluie, pas trop de vent et pas de houle très haute. Donc je vais sur le workboat, le petit bateau, et j'échantillonne le DMS dans la micro-couche de surface, donc qui est le top millimètre de la surface de l'océan. Donc j'ai développé une nouvelle méthode pour mesurer le DMS, qui est donc ce gaz, dans la micro-couche de surface, parce qu'il n'y a pas de méthode qui permet de bien échantillonner les gaz dans cette micro-couche là, appropriée pour les gaz. Alors là, on a collecté de l'eau de la surface du micro-layer, donc c'est la micro-couche de surface. Et maintenant, avec une partie de l'eau qu'on a récoltée, je vais faire des incubations à la lumière. Donc je vais mettre, j'ai des ampoules comme ça qui sont noires pour faire un contrôle, et d'autres qui sont transparentes que je vais remplir avec l'eau. Et je vais voir quel est l'effet de la lumière sur le DMS, donc sur le diméthylsulfide. Donc c'est le gaz que j'étudie et qu'on analyse ici après. Je vais avoir une idée de est-ce que le DMS, est-ce que la lumière va plutôt oxyder le DMS ou est-ce qu'il va en produire, ou est-ce que ça va favoriser sa production. J'en fais 6.
I'm a graduate student from Colorado State University in the US, and I'm here on the Tangaroa measuring ice nucleating particles and also airborne DNA from microorganisms that come from the ocean. And we're interested in these things because they impact clouds and reflection of solar radiation from the surface of the ocean. I've got one instrument in that container down there measuring ice nucleating particles in real time. I've got 3 filter samples out on the front deck that are measuring ice nucleating particles, DNA, and trace metals, and another filter sampler that is running on the very bow of the ship looking at airborne DNA. The only data location.
My name is Andrew Mariner. I work in the biogeochemistry group at NIWA in the Ocean Atmosphere Labs. I mainly work on dissolved gases.
Oh, that's super high resolution for us though.
Oh yeah.
We're going day by day.
Day by day. So my name's Stephen Archer. I work at Auckland University of Technology in Auckland, New Zealand. I am on the ship to collect ambient aerosols, looking at the microbial composition of the air. So I'm looking at the bacteria, at fungi, and all of the life that is in the air, and trying to link that with where it's coming from.
Hi, I'm Maya, and I work at LAMP in Clermont-Ferrand, and here I'm measuring the number concentrations of aerosol particles in different sizes and different chemical compounds in the air that could form these aerosol particles.
Yeah, could even go over there depending on what the weather's doing, to cut across this storm that's coming through.
Yeah, is that coming? That's coming from the south.
It's pretty much coming across.
Oh,
and so we've basically got to try and
hightail it up to
yeah, but it's even according to the windy, it's even going to spread up there. So I'm wondering whether we should just try and cut across it, go from here where it'll be calm, or
just sneak off home for a few days and top up some supplies.
Don't say in terms of the water analysis, we've been doing it in several different ways. We've been sampling the surface layer when we've had people out on the workboat using different techniques to collect water samples, but we also use the CTD, that's the large rosette. It has 24 10-litre bottles on it, and they collect water from the upper 200 metres of the water, and that allows us to actually look at the underlying biology and biogeochemistry, and then we can relate that to what's going on in the surface.
So they usually like it somewhere around 60 metres per minute dropping down. I'm at 53, doesn't matter, but around the 60 metres a minute mark coming down.
Stop there.
And stop there.
And stop there.
And stop there.
So what we do is a routine thing when we're analysing, or at least when we're sampling from the CTD, we would normally sample at about 6 depths in the upper 200 metres, and that gives us a good idea of what's going on in the surface mix layer. The surface mix layer is really the important part because that's where the phytoplankton live, that's where they have enough light to live and grow, and so we're really interested in their distribution in that surface mix layer, because once again that influences the biology, and subsequently that influences the amount of particles and gases that are released into the atmosphere.
Hi, I'm Neil Barr. I'm here on the Tangaroa during this trip to look after the acid tanks outside, do some filling and emptying and cleaning, also look after the CTD outside.
Yeah, basically
My name's Carl Safi. I'm a scientist from NIWA in Hamilton. The instruments I'm running here, this one here is a flow cytometer, and it's looking at picoplankton, bacteria, and the smaller end scale of the phytoplankton. And here we have a flow cam, and this instrument looks at some of the larger cells and gives us a general idea of the different speciation of what's in the water. As far as the tanks are concerned, we're interested in how the two tanks may evolve different populations of all these types of different microbes, from the bacteria through the larger phytoplankton and perhaps even some of the microzooplankton. I work midnight to midday, and we're sharing a shift with another group, and we're all running these same instruments. We're looking at chlorophyll, nutrients, and all the basic chemistry of the water column, and so we can understand those changes and relate them to what we might be measuring in terms of gases as well.
I'm Wayne Dillon. I'm a PhD student at the University of Otago, and I'm here helping out on the research, filtering and collecting samples. I'm working with Cliff Law, and I'm doing the night shift, midnight to midday.
Hola, mi nombre es Antonia Cristi, soy estudiante de doctorado en NIWA, en Wellington, y acá estoy a cargo, junto con Stacy, del muestreo de agua durante el crucero SEA2CLOUD. Y aparte de eso, yo estoy a cargo de tomar muestras para DNA que nos van a servir para luego tener una visión de la diversidad de la comunidad que estamos viendo.
My name's Stacey Depler. I'm the Marine Biogeochemistry Technician at NIWA in Wellington, and what I'm doing on here is I'm doing looking after the surface water sampling. So what we're doing is taking samples of water at regular intervals on our underway system, but we're also sampling from the CTD and the workboat and some of the ACIDS experiments. So these pictures taken from the tank experiments, the ACIDS tank experiments, from the first experiment on the last day. So just checking the data now to see if we can see any trends in the size differences.
Sorry, what was that, Catherine?
Okay. You don't have the data. But you'll pay it. So we're now actually around 12 days into the voyage, but unfortunately we're going to be having to end it soon because of the unprecedented global event that's happening around the COVID virus. And this means that we're finishing about 2/3 of the way through the project, or certainly the voyage. And you know, we've achieved about 2/3 of the work. It's been quite successful despite the fact that we've had a lot of rough weather which has held us up at different times, but we've certainly got some interesting results from the tank experiments where we've seen different changes in the biology of the water in the different tanks, and we see a response in the atmosphere above those tanks. We've also had the workboat out 4 or 5 times now, and we've got some good results from that. And also we have our background ambient measurements which have gone on continually throughout the voyage, and so we'll be piecing together both the atmospheric data and the waterside data to see what that tells us. So all in all, despite an early finish, it's been quite successful.
Néanmoins, nous avons collecté une grande quantité de données avec des situations contrastées au niveau de la concentration en phytoplancton le long du trajet. Au niveau des mésocosmes, on a réussi à mettre en œuvre 4 expériences différentes avec des eaux différentes. Alors, on est très content de ces expériences en mésocosme. C'était pas évident au départ de mettre en œuvre des mésocosmes sur un bateau à cause des effets de roulis du bateau, et donc il fallait absolument que les capteurs ne soient pas émergés dans l'eau, les capteurs atmosphériques. Donc ça, c'était un pari difficile qu'on a réussi à relever. Tous les instruments de mesure ont fonctionné correctement, donc on possède maintenant une base de données assez intéressante.
Donc je trouve que 4 semaines c'est un petit peu lent. 3 semaines c'est bien parce que souvent la première semaine tu t'adaptes, la deuxième semaine tu as une bonne routine, et la troisième du coup tu continues sur la lancée. Mais tu n'arrives pas encore au moment où tu es fatigué et tu en as marre parce qu'on est quand même enfermé sur un bateau, donc c'est fatigant. C'est avec les mêmes personnes aussi, on voit pas grand monde. Mais bon, pour le moment ça se passe bien, et ouais, à mon avis 3 semaines c'est bien. 2 semaines ça aurait été trop court.
I hope you didn't get that.